this information's been out there for years. Quite frankly, actually, what's not in my list of documents is currently, you'll probably learn about this, we are releasing a white paper on this topic as well that will basically go through all these calculations and stuff. So the material, the next series of slides you're going to see is stuff I did not write. This has been part of our normal SCCR lunch and learn programs and training material for years. It seems to be the best way to skin this cat. But let me share with you the reason why we talk about SCCR, and that's what that really cool explosion picture is. Well, it's cool unless you're the guy standing in front of it. But what is short circuit current rating, right? And so I'm just going to kind of quote the NEC. Article 100 kind of talks about it, right? It's this prospective symmetrical fault current at a nominal voltage to which an apparatus or system is able to be connected without sustaining damage exceeding the defined acceptance criteria. In a nutshell, this is what can be connected to a system when it blows up. It doesn't hurt anybody. Fire and shock protection. What brought this to light was some requirements in what standard? Anyone know? Oh man, this guy is really collecting JJ points. You're kind of like the, who's that guy in Jeopardy, the Jeopardy superstar guy? What is his mic something? Yeah, you're the Cliff Blaven of our he's my sidekick. It's a little old fat there. Yeah.
Not been in my kitchen.
Yeah. All right. So in essence, you know, it's the maximum fault current that a component, like a breaker, can withstand. You know, without hurting somebody. And we're really talking here about personnel safety when it comes to maintenance. And if you look at the numbers and statistics, fundamentally, what do you think the predominant source or reason for arc flash is? Well, it's up there on the slide.
Short circuit.
Short circuit, but what's the root cause, I guess, maybe?
People.
People is one.
Loose connections.
Loose connections and aging infrastructure. Just, you know, like, I don't know, my home is almost 100 years old. When I go up and even change out a light fixture, what kind of wire am I finding? I'm finding the, I don't have knob tube. My knob and tube's gone. But what I'm finding in some of the fixtures, I'm finding the cloth insulation. And as soon as I unscrew the wire nut, it comes down in dust and I got a big old conductor that's sitting on like that. Right? That's really the root cause, is it's old or damaged insulation. Just again from years and years of fatigue and insulation, dried out and stuff like that. And so that's obviously the fire and shock hazard, and also the catastrophic solution of a full-blown arc flash, right? We call it a bolted fault. What really causes that nastiness right there is this idea, if we understand the physics of power sources, it usually comes from a transformer, correct? And a transformer, if you were to short a transformer, you're basically bringing the impedance to almost zero. And that is in the divisor, that is in the denominator of the short circuit calculation. And when you try to divide zero into something, what do you get? Infinity. And from a theoretical perspective, you have infinite amount of current for a brief period of time flowing through this poor little circuit breaker. And that is the result. You get the shrapnel. What you're seeing there is basically the copper and all of the innards of that breaker flaming out and becoming shrapnel. Yes, sir.
Also, though, it happened across phases too.
Absolutely.
Phase.
That we call it a bolted fault.
Yeah,
It's phase to phase. Yeah, and unfortunately it would result in if they drop a tool across the incoming service or something like that, right?
Lock wash that fell across the phases.
Yeah, and unfortunately, yeah, those are circumstances. But what I want to clear up is that bottom saying it's not to be confused with the breaker's interrupt rating. Now I'm going to start, this next series of sections, I'm going to start throwing out some jargon. I'm going to be throwing out short circuit current ratings, I'm going to be throwing out interrupt ratings, and we're going to talk about let through currents. So we got to be real clear of the terms we're using here. So I'll try to be very methodical as I work through these explanations. But half of the confusion around this topic is mixing and matching what the physics is and what some of these terms are. Breakers have interrupt ratings, and they do play a part in the overall panel SCCR when we are doing current limiting rules, and I'll try to explain all that stuff to you in a second. Okay. The deal here though is where, if you want to connect the dots back to where this is important, it's NEC Article 409. This is the one where It points out that you're, as the panel builder, are required to label a panel with a short circuit current rating. It does not prescribe what the rating should be. Where does that come from? Any thoughts? Yeah, from the power evaluation, from your customer, ultimately. They need to know what it's connected to, right? And so sometimes that is not information you're given. And you may even say, but it's on JJ's inquiry form. Yeah, it should be there. No, not always. You're not always given that data. So that's why they'll just say, give me 65, right? They're doing the old peanut butter approach, which is fine and all, but it gets to be sometimes expensive and hard to accomplish. Yes, sir.
So when you're not given that information, how do you do the calculation?
Well, you don't need the available fault for the calculation. Your user does for their NFPA 70E stuff. Basically what they will do is prescribe a peanut butter. Like they'll say, oh, just give me 65. And then you label it 65 and I'll make sure it doesn't get attached to anything less than that, is what they'll say. But quite frankly, 65 is overkill. There are many cases where you won't get anything over 25. But you don't know that. They don't know that, so they'll probably just say, they'll prescribe a very heavy short circuit current rating requirement. It's the peanut butter engineering approach.
So you do the calculation based on the assumed 65?
Yeah, based on a target. Yes. So you're saying my target is 65. So this is your target rating that you're going to.
Well, I know what the customer's going to do with that.
What's that?
I know what the customer's going to do with that. Absolutely nothing.
Correct. But according to the NEC,
they'll just say, oh, there's a sticker.
yeah. But according to the NEC now, and back into that article 409, they are required to base their installation on a real calculation. So somewhere in the regulatory chain, they are supposed to do a true fault calculation.
But that's why I thought that the actual sticker has to be done by the end user, not by the panel builder.
Now, this is a UL requirement. It's a 419 requirement. You have to put what the available fault could be. And it's up to them to install it to ensure that it's not subject to a short available fault current greater than that. So I have many of my customers that don't want to go through all this mess, and they'll put 5 kA on the label. And then they put the onus on the customer to not install it above 5 kA. Now, is that a commercially viable solution? Maybe, maybe not. Some customers, like they'll do is they say, well, I'm going to pick 65, because that's a very high threshold. And it's up to them to not install it at something greater than 65. The onus of the installation is still on the user. I don't know if that clears things up for you.
Yeah, it's just that the sticker on the panel is supposed to help the maintenance people to know what type of clothing and gear, or what equipment, personal protection they need in order to work in that cabinet. So if I'm putting a sticker on there based on whatever,
well, actually,
prior to the installation,
so your panel rating is not based on their suiting up is not based on your panel rating. That's based on the available fault of the service into the panel. And in addition, your panel rating needs to ensure, the installer needs to ensure that it's installed so that it does not exceed what you say it will exceed. So you're the one that knows the branch protection and the feeder protection and can do this evaluation to the SV4. You put a label that says it shall not exceed 65,000 amps at 600 volts. It's up to the user to install the panel, look at the sticker, and go, yes, I'm not putting it at anything greater than that, based on a true evaluation of the installation, which is, again, information you're not privy to sometimes. So you just got to basically rate it based on the components you got in your box. Does that make sense?
Your box is safe up to
Yeah.
65 or whatever.
Yeah.
So they have to limit it.
right, but I thought it was up to the owner, or the owner to make sure that the
Yeah.
sticker that's on there is based on what equipment up ahead of it that they
It's based on their available current of your service. So you have to limit their feeder breaker to be below
The
65.
box only represents the components.
Ideally,
But we have no way of knowing that. I thought the rule of the short circuit was that they have to do it based on the installation.
The only paradigm we got is it says if we're in the box, looking at only what's in the box, we can evaluate what the componentry is able to withstand from an available fault. And that's what the sticker says. Now, for the end user doing the installation, your sticker value is a piece of data they need. The available fault calculation is a piece of data they need for proper application. But your job is really only what's in the box and what the available fault it can sustain without the damage, based on these calculations.
And we can match their feeder circuit to that rating.
And then they match their feeders. Yeah.
Which is why we don't provide an FBA labels on anything that doesn't come out of our shop.
Yeah.
We've had customers want us to come through and say, can you put NFPA arc flash
Yeah.
ratings on all this equipment?
Or
You don't have all the
data
data
for it.
We're like, well, first of all, our insurance company doesn't want us to do that. And the second thing is there's a lot of liability behind that. And what we find is people call in GE, Everett, they have whole groups that do that. And they usually tend to overrate them. Like, you know, I gotta put a balloon suit on to change a fuse because of the liability.
So I don't know if that clarifies it or not, but so fundamentally, if you look at the SB4, it's broken down into 4 basic steps. Sounds simple, right? Oh, it's only 4 steps. Well, one of them is even marking the panel, which is pretty straightforward. So really only 3 steps. But we'll see quickly here that it's not always the easiest step. So step 1 is talking about all the power circuit components. And why did I underline that? Remember back at the beginning of the UL combo, I had said you need to be very clear what a control circuit is versus a power circuit. And it all depends on the load that you're attaching to it. So if you attach motors, it now becomes a power circuit and becomes susceptible to the requirement of SB. And that's what you don't want to do. But here's the deal. So all the power components, including disconnects and, right, shall have a short circuit current rating in KA and voltage. That's really what it's saying. Now there's a handful of exceptions here, like power transformers and reactors and things like that. Very important is number 4. For those of you who use ferrules, and some do, some don't, for many years, the use of ferrules, which are crimp-on lugs for wire containing stranded wire, people were asking, well, does that impact my short circuit current rating if I use ferrules on my feeder wire? It does not. Okay, that's a clear now. It had several volleys of different answers to that. They have clearly gone in the exception here and said it is not. The other exception that I want to clear up here is exception number 5 under EMI filters. That one is still in the air. They're still debating that one. That's why in the previous section when I showed you things that are not being implemented yet, that's up in the air. So let's just kind of talk about step 1. All right, so this is the short circuit current rating of a feeder or branch component shall be established by one of the methods. So we're talking here of a component. So this would be like, for example, the first one is the short circuit current rating marked on the component. So this would be a breaker, an overload, a contactor. They have a rating marked on it, and it's usually a manufacturer test rating. So on the side of our contactor, you will see what our short circuit current ratings for that component is. Now, you could also grab data from what's called the UL standard default ratings, or there's a table in SB4, which you'll see in another slide, that has just pre-canned ratings for typical components. Again, usually fairly on the conservative side, but that is another source of data if you don't have the manufacturer data for the component. The third step is the one that we prefer as a manufacturer, and I'm sure our competitors do as well. It's what we call the combination test rating. This is where we take a collection of branch circuit components, circuit protection with a contactor with an overload, which are 3 discrete components. We test them as a combination. You know, we basically blow them up in a lab, and then we can ascribe a combination rating to that assembly. So A is an individual component from the manufacturer. B is individual component rating from the back of the UL book. And the C is the combination rating of an assembly of components. Again, it's a one-stop calculation that might cover up to 3 devices. Okay, all clear on that? So that's step 1. It's one of those 3 choices. Here's an example of a component. I know hard to read from the slide deck, but it just gives an individual short circuit rating. Here's an example of the table in SB 4.1. You can see here, like example, motor controller. Most often, you're going to see ratings by default of 5 or 10, predominantly for most of your power components. And then the third one is an illustration here. This is an example from our short circuit current rating tool of a manufacturer combination test rating. And competitors would have the same, Schneider, Siemens, whomever, where we test a combination of a contactor with an overload relay with a circuit breaker, fuse, and whatnot. Okay, so one of those 3 bits of data is what you need. Okay, some other things for step 1 that you need to be aware of is the high fault rating of the feeder or branch circuit is specified, shall only be used in the specified branch or when the protected device is provided. That basically means that you look at the high fault current rating of the branch in conjunction with the protection of the feeder circuit in protection with the branch, right? So we can look at the branch circuit as a limiting factor to the available fault of the panel as well, right? And so we also look at let-through currents, which we're going to dive through in a second here for current limiting devices. So let's talk about step 2 when it comes to this idea of current limiting. What I have highlighted here is the feeder of a power circuit. And again, when we try to leverage current limiting rules, it's important to keep in mind that we're doing this in the feeder for the various downstream branches. So what's highlighted in red or pink here is the feeder. These individual loads are branches. So what we do is we go through step 1 for each branch. Right? So we got to know the SCCR. If it's combination rating, it's simple. Right? Boom, 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 boom. That's why a lot of times mixing and matching competitive products sometimes doesn't result in a simple solution. But you'll see here there's 3 ways to do current limiting. There's current limiting through a power transformer, there's current limiting through the use of a current limiting breaker, and there's current limiting through the use of fuses. I can tell you right now, fuses through their physical characteristics are inherently current limiting, and they kind of get the benefit of the doubt according to the UL document. They've been viewed as current limiting devices for many, many years. As with circuit breakers, current limiting circuit breakers are engineered devices for current limiting, right? So you have to look and review trip curves and let-through values from the actual manufacturer. So just pay attention to that. There's 3 ways. So let's talk about the first way to do current limiting. That is through a transformer. This is the most simple and brute force way of current limiting. A transformer, either single phase or 3-phase will current limit. There are some calculations you can do here, right? There's some formulas that you can determine, or if you would choose to just use a lookup table, you assume an impedance of 2.1% transformer, and these tables then become your source of data. And you can see here in an example here of a single phase or versus a 3-phase transformer, and you're able to look at the available let-through current of that transformer. So what you can see here, for example, we have a 480 volt Y transformer at 100 kVA is 7,180 available short. So that 100 kVA transformer can, at 480 volts, can pump out roughly 7,000 amps of short circuit. Well, if I have a 10,000 amp device down below, that's okay. But if I only have a 5,000 amp available fault withstand, that is not good. So again, you would square what components I have in my branches and feeders with the source that it's giving here, in this case, 7,000 kVA. The second way you can power limit is with a circuit breaker. And just like Casey had pointed out his thing, I started chuckling when you went through that one paragraph, because I found the same exact rationale here. One of my frustrations with dealing with the SB4 is just the fact that it's poorly written English. It's long run-on sentences with a lot of complicated jargon thrown in the mix just for good measure. So for me to digest this, I had to almost go through and break apart the sentence, and that's why I color-coded and underlined things for you. I don't expect you to all consume all this information right now. The lack of silence that I always get during these presentations is because you just don't know what I'm saying. And sometimes you need time for this to sink in. What I would encourage you to do if you're trying to understand this is go back to this slide and read the color code, and so I'll just kind of work through it for you. So the short circuit current rated selection for the feeder. Okay, so we're talking about feeder current limiting. When all of the individual branches, so in order to determine the feeder current limiting capability, we need to zoom down to the branch, down here, and there could be multiple branches, remember, right? Okay, when all these components have a short circuit current rating not less than the published peak let-through current of the circuit breaker. So a data point you need to do this evaluation from a manufacturer of the breaker is a thing called a peak let-through current. You all understand that if you're subject to an available fault of 65,000 amps, that these are engineered devices that have a lag in response. And you could get a partial cycle of current that comes downstream and blows these little guys up downstream. That's what we're talking about for peak let-through. It's a partial cycle, okay? Now, so that's the part in blue. And, so it's not an or, it's an and the short circuit current rating of any combination motor controller on the load side are not less than the interrupt rating of the feeder breaker. What that is saying is we need to look at the interrupt rating of this breaker, okay? Okay? So we have to look at two things, peak let-through, and we have to match the interrupt ratings of the branches to the feeder. Okay, so if you buy a current limited breaker that has an interrupt rating of 65,000 amps, and you want to claim the peak let-through and the current limiting rules that that breaker provides, every one of the branches needs to have a matching interrupt rating. What cannot happen, and people who misinterpret this go, oh, I got one of them current limiting breakers that I paid a lot of money for. I could put a whole bunch of crappy branch protection down below it, and I'm protected. That is not correct. I have found this is actually a very lofty requirement. Quite frankly, these current limiting rules are exceptions, not rules. They should really call them current limiting exceptions to the circuit design. You need to have a well-coordinated set of interrupt ratings at the branch that are as good or better as the feeder, in addition to looking at the peak let-through of the branch, of the feeder, with all of the components down below. You get that? I know you don't. I don't know how else to explain it.
Do you have an example?
Yes, I have 4 examples.
All right.
They're in this PowerPoint. I have 4 specific examples. I give you 4 more as individual sheets in that in the files. You have 8 examples to reference. I honestly, I don't know other ways to do it than to maybe just look at the examples and think that this is very theoretical stuff. So, my clicker go? My clicker went haywire? Oh, nope, someone hit me on Skype. Got the Zessen. Hey, dude. I thought I shut off my Skype. All right, so let's talk about this. So one of the pieces of data, a lot of people ask me, where do I get this data? You get that from us. So a breaker vendor will provide you with those 2 pieces of data. You're allowed to use the manufacturer's curves for this evaluation. So here's an example of one. This 65,000 amp rated breaker has a 20,000 amp peak let-through. That data is derived from the trip curves here that you get. Right, so you make that evaluation by reading the trip curve. You then have to make sure that everything downstream is better than 20,000, either as a combination rating or as a component. Then, if that's the case, so that's your first hurdle. If that's the case, you then go up to each branch and go, is each branch, is its interrupt rating as good or better as the feeder? Yes, those are the two ands, hurdle number 2, then you are able to claim it. So I guess what I don't want you to leave you with the impression is you can't use this to mask, we'll say, less than adequate branch protection. Sir?
No, so basically that thing is gonna let that much amperage through.
Yes.
And have to calculate for everything behind it.
Yes.
Because it's not gonna fully
Correct.
stop them.
Because there's a lag in its response. It's an engineered device. Now, the next example is fuses. Fuses, this is accomplished through material, physical material. The fuse, the inner material, responds a lot faster because you don't have to have the sensing and all this stuff. It just,
Like slow blows will
it's the physics.
last longer.
Yeah, exactly. It's the physics of the material. So it's the properties of the material that are in play here. And so baked into the standard, there's a lot more liberal, I'll say liberal is not the right word, there's a lot more generic characteristics that are baked into the standard because these have been around so long. Right? There's a lot of history with them, so they kind of get the benefit of the doubt. But the philosophy is the same. You can go to the UL book, and instead of going to the manufacturer like Bussmann or Faraz or whomever, you just basically go to the book, and typically you'll use the 100K application because they're typically something over 50. And you'll go down, and so in our case, if we're using a 25 amp J fuse, the peak let through is 6 amps. So then again, we apply the same technique. We look downstream of the branches and go, can everything down below that sustain 6 amps? If that's yes, that's hurdle number 1. Then we have to look immediately upstream to the branch protection. Does that have the same interrupt rating as the feeder device? Yes, that's hurdle number 2. And so we can claim current limiting rules. Okay? So for example, and again, here's another long run-on sentence, step 3. So for each branch, the smallest short circuit current rating of all power components on the load side of the branch protected device and the control circuit overprotection shall be determined and compared to the short circuit current rating of the branch circuit provided. The smaller shall be assigned to the line side of the branch protected device. In other words, use the lowest rating of a component or branch protected device. The other thing that's saying is power supplies and fuses, that's what they're in the corner there, they are exempt from this application. You carry the calculation up to the fuses and or breakers that are protecting the transformer. So if you have a good set of fuses or a good set of breakers protecting the transformer, that is all you need to account for. The control circuit branch carries the rating, the interrupt rating of the protected device. Yes. A lot of words there. But then you have to rate the whole panel. So this is boring stuff. The sticker is the easy part. Let's talk about a couple examples. Maybe that will bring this home. So you have 4 examples you're going to find in the PowerPoint slide. You have 4 more examples that are in the handouts. I just grabbed some for instances. So this is all just kind of word problem stuff that I made up. We have the default ratings for this first branch. We have, and it's a mix and match of 5 and 10. So basically this branch will carry 5. Combo rating, combo rating, combo rating of 65. So each of these other branches carry 65. And the breaker upstream of the power of the transformer is a, let's say one of those mini breakers, it carries a 10. So we're at this point, this guy's a 5, 65, 65, 65, 10. The manufacturer data on this breaker is 65 kA, but the power distribution block is a 10 kA. Okay. So what is the limiting factor? Overall panel is 5 because of the CB1 and overload and contactor 1 are the limiting factors to 5. So I get asked a lot not only what my rating would be, but what would I do to bolster my current rating? In essence, you would want to swap that guy out to a fully combination rated device. swap out that breaker that's protecting the transformer. Another very common pitfall is in the feeder, when you do power distribution in the feeder. Power distribution blocks sometimes will mess you up. Two ways you can get around it. Number one is we list our circuit breakers and fuses and feeder power distribution blocks as a combo rating. Many of them are 65. With fuses, they're 100, sometimes 200. The other way to get around it that I found is real helpful for optimizing not only panel space but cost is the multi-tap lugs that go on breakers. Have you started using these? They're handy because they're not, they're one less component that's on a backplate. But number two, if they're a UL listed accessory to the breaker, they carry the same rating as that breaker. So that's helpful. Okay? So that's one very common pitfall around feeder power distribution that I see messes up SCCR. That if you were to use, and again, we have them, our competitors have them, so but again, I wanted to share that. Yes, sir.
The blue square there is
Yep.
isolated because of the extra water flow.
Yeah, so according to UL and SB 4.2.1, he's exempt from the calculation here. And so that's why I just showed that you only have to stop, you stop basically at its protection line. Yep. And similarly now, this is a similar example. Well, the only thing you'll notice here is I went to a fully combination rated, maybe I went with a power distribution block that's, on multi-tap lug type thing. So it carried a combination rating of 35. And you see each of my branches were 35, but this breaker over here, I'm still cheaping out using a little mini breaker, and that's 10. That fella right there would be our limiting factor. And so we would want to go with 10. Or we want to swap him out. If we wanted to go with 35, we could put something different in there. But 35 would be the most we could ever get because of this manufacturing. Let me show you an example of current limiting with a circuit breaker. So again, up in the right-hand corner, I show that you would have to grab the manufacturer trip curve data, right? And you would have to read that chart and come up with two pieces of data. One of them is the interrupt rating of the device, and one of them is the peak let through current of that device. In this case, it's a 65 kA and 15 kA. That needs to be known because that is what the downstream components are subjected to. So then we look at, the evaluation kind of skips over the branch and looks at all the components downstream, and is it as good or better than 15 kA? Well, the one here for circuit number 1, we got 20,000, so yes. We have a combo rating, so that's good there. We have another combo rating of 65, but the VFD there is 20 kA. We have a 20 kA drive rating. So in this particular case, all of the downstream devices are as good or better than 15. We then go one notch upstream and see all of the interrupt ratings match what the feeder is, and so we can claim 65. So again, I want to use this example to reiterate that just because you try to leverage current limiting rules with a fuse or a breaker does not mean you can cut corners on the branch protection. I think people are left with that incorrect analyses. Hitting this is really hard. I've rarely successfully met current limiting rules in a real world application. It's just a pain. If you really want to do it, I had one customer that was insistent upon it. We actually convinced them just to install a big old transformer in front of everything. And he did that. Yes, sir.
On your last slide there, you were trying to reduce the rating of the panel. You wanted to try to reduce that main lug, the 65 kA. You can reduce that to your 20 kA to match your lowest one, then all your other ones would be satisfied as well?
Which one again?
For your main one that has a lug at 65 kA, if you were to replace that breaker with one that was rated at 20 to match your other branch
well, no,
VFDs.
No, because this guy is setting the limit for the interrupt rating.
Right. So, but that isn't that the short circuit rating for the arc flash for the panel? or am I missing that? So if your customer gave you a requirement, they only wanted a 20,000 rating, you would change the main breaker to max?
Oh, yeah.
To lower that?
Absolutely, and then if they're giving you, I mean, that's a reasonable bogey. 20,000 is reasonable.
Yeah.
You probably would not even need to mess with current limiting rules,
Okay.
honestly. Yeah, I find 25 or 35 is very reasonable. I remember when somebody did the math, like the real math, on what available fault is at really 65, the size of the transformer was astronomical. I mean, it's crazy. I mean, I think it's probably more around 25 to 30 is probably a reasonable number.
Then just to make sure your let through doesn't,
Yes, yeah.
that'll iterate back down.
Yeah, that goes down everything, all the branches, yeah. So the power transformer is kind of the simplest one, because like we had said in the chart, you look at the power transformer, right, and you just look at what its peak let through is, and they're very, very limiting. And so you basically just put a power transformer in front of everything, so even if you had to use a 5 kA panel in this case, you would be fine because the available let through is 2.4 kA. So in this particular scenario, I'm talking as if I put a transformer inside a box. So I'm looking inside the panel. Of course, somebody in my other class said, that'd be a pretty big transformer to put in a box. I mean, yes, it would. So we can kind of talk about this in two scenarios. Number one is if indeed you did put it in the box. The whole panel would carry 65. Because all of my branches down below past the transformer are well above the 2.4 kA, even at default. In which case, you're limiting yourself to what the to the main circuit breaker number 9 there, so you could claim 65. So then the guy proceeded to say, yeah, but what if that transformer was separate from the panel? Like I say, like a lug-only panel, or right? Okay, well then what I would put on this panel is 5 kA on the box, but I would reference the fact that the upstream current limiting is achieved from a 30 kVA transformer, and the peak let through of that guy is only 2.4. So we're back to the fact that it would be a default 5 kA is more than sufficient to meet the peak let through of this scenario. So however you want to skin that cat is a reasonable way to do it. All right.